Hi students, welcome back. Coming to the next topic in the subject, Advanced Computer Architecture is Arithmetic Pipeline Design. So before going to understand what exactly this arithmetic pipeline design is, let's recall the introduction part of this arithmetic. So in the modern digital computers, the arithmetic calculations is performed by using either the fixed size memory words or the registers. So that we all know that. So now whatever the modern processor that we are using, it consisting of fixed and floating operations. Floating point operations are going to perform the modern processors. So fixed point operations are nothing but you also call it as an integer arithmetic. Okay, integer arithmetic. And what about this floating point? So this floating point arithmetic operates over increased dynamic range of numbers. So this fixed point or the integer arithmetic offers fixed range of, let me write that point. It offers fixed range of numbers that can be operated upon. Okay, so this fixed point operations or offers the fixed range of numbers that can be operated upon, whereas the floating point operations operates over increased dynamic range of numbers. So what do you understand from this? So if you take the computer arithmetic principles, it consisting of a fixed point unit as well as a floating point arithmetic operations. It has to perform fixed as well as a floating point. So the fixed point will offers the fixed range of numbers. It is only to perform the fixed range of numbers that can be operated. Whereas the floating point operation operates over increased dynamic range of numbers. Okay, and these two, the fixed and floating point operations, are very often performed by separate hardwares on the same processor chip. In the same microprocessor chip, okay, in the same microprocessor chip, it is having a separate units. One is for the fixed and another is for floating. Okay, so arithmetic operations are going to performed in the ALU, the arithmetic logic unit. So this the microprocessor. In the microprocessor, we are having a separate hardware will be present. One is for the fixed and another is for the floating. Okay, so first let's discuss about the fixed point operations, and then we will see the example on the fixed point operations, and later we will see the floating point operations and the example further. So first get a complete clarity on what is this fixed point and the floating point. If you get the clarity on these operations, then you can easily understand what do you mean by the arithmetic pipeline design. So because in the arithmetic pipeline design, we are going to perform the operations on only the fixed point as well as the floating point numbers. Okay, so now let's have a look on what exactly the fixed point operations. The one thing that you have to be remember that the fixed point operations are nothing but there is a fixed number of digits. A fixed number of digits, that is the numbers, either the binary numbers or the decimal numbers, whatever it may be. There is a fixed number of digits after a decimal point. So that you call it as a fixed point operation. There is a fixed number of digits after a decimal point. Okay, so the fixed point operations can be either unsigned numbers. It can be performed on unsigned numbers, and we can also perform on the signed numbers. That is unsigned fixed point numbers and the signed fixed point numbers. Again, these signed fixed point numbers are divided into signed magnitude, ones or twos complement. Okay, so a fixed point operations either can be performed on the unsigned numbers as well as the signed numbers. So unsigned means, you know, it is a positive numbers, the positive numbers or the unsigned numbers, and coming to the negative numbers, so that is a signed numbers. So that can be of two types. Either you can perform the sign magnitude operations, or you can perform the 2's complement or 1's complement notations. You can represent that in 1's complement or 2's complement notation. Okay, so the most of the computer used today's was what? A 2's complement machines. Most of the computers will go with the 2's complement, because it is a unique representation of all numbers including 0. So that's why most of the computers will prefer the 2's complement. So up to here, is it clear for you? Means a fixed point operations can be either the unsigned and the signed. I'll tell you what is this unsigned and signed with an example. Okay, so here our main motto is we have to understand that arithmetic calculations can be performed on the fixed point as well as the floating point numbers. So let's see about this calculations. Then you will get the complete operation on that. So generally there are 4 arithmetic operations. So what are that? The 4 primitive arithmetic operations. What are the 4 primitive arithmetic operations? Can you guess? Yes. Addition, subtraction, multiplication and the division. So everyone knows about this. So there are 4 primitive arithmetic operations in general represent the addition, subtraction, multiplication and division. Okay. So here we are talking about the fixed point, right? A fixed point numbers for addition and the subtraction, if you take 2n bit integers, suppose if you take the 2n bit integers, so it produces what result? It produces n bit result. So that means if you take 8-bit, 2 8-bit numbers, the output is 8-bit only. If you take 2 16-bit numbers, if you are trying to perform 2 16-bit numbers addition or subtraction, you will get only the 16-bit result if you take the addition and subtraction. Then what about the multiplication? In the multiplications, if you take 2 n bits, okay, if you take 2 n bits integers, the result will be what? Can you guess? The result will be 2n. That means if you try to multiply 2 8 bits, you will get the result as a 16 bits. That means if you are trying to perform a product operation on 2 n bits, you will get n plus 1 n. That is a 2n result. Okay. Then what about the division? So in the fixed point calculations, the approximate result is expected is fixed point division is with rounding or truncation. So it can be do whatever the value you will get, you will have to do rounding or you have to do truncation, because you will get only the approximate result if you perform the division operation. Okay, so this is about only the, I'm just talking about the 4 primitive arithmetic operations. So if you perform the fixed point operation on the 4 arithmetic operations, addition, subtraction and multiplication, you will get this type of the result. Now let's have a look on what is this unsigned fixed point and the signed fixed point. Okay, then in the next video we'll discuss about the floating point operation also. So let's take an unsigned fixed point. So the unsigned fixed point, here the number you can take, whatever the number we are taken, this number is divided into 3 parts. One is the signed part, and another is the integer part, and another is the fraction part. The complete number is divided into 3 parts: signed part, integer part, fraction part. Suppose let's take, we have to represent example. Let me explain you with an example. Represent a fixed point representation of unsigned binary number. Let's take this is my unsigned binary number. So using, they are giving a condition using 4 int bits and 3 fraction bits. So what do you mean by this? This 4 int bits and 3 fraction bit represents the decimal. To represent the decimal point, this condition is necessary. This condition is necessary. Why we require this condition? To represent the decimal. Okay. Now let's first divide this, means represent this fixed point number by using unsigned binary number. So this is 0 1 1 0 1 1 0. So here the first one, whatever the bit is there, this is the most significant bit. This is a signed bit. Okay, if it is 0, it is a positive number. A signed bit is there. Okay, so using 4 integer bits. So total in this 4 integer bits means take only the first 4 numbers. Okay, and what are the fraction bits? 3 fraction bits. The remaining numbers are 1 1 0. So I represent the decimal number. So with the help of this information only, I am able to represent place the decimal point. So 4 integer bits and 3 fraction bits. The first one is a signed bit, which is a positive number. So convert into decimal. Let's convert into decimal. You know this is a binary number. How you are going to convert into decimal? You all know the calculation. 0 into 2 power 3 plus 1 into 2 square plus next 1 into 2 power 1 plus 0 into 2 power 0. And coming to the after decimal point, 1 into 2 power minus 1 plus 1 into 2 power minus 2 plus 0 into 2 power minus 3. So if you perform the calculations, you will get 6.75 decimal number. So this is the way you have to represent the unsigned fixed point number. Okay, so let's take the signed fixed point number. So I think you get complete clarity on what exactly the unsigned fixed point number is. Now let's have a look on the signed fixed point number. So once you get the representation clearly, then you can easily understand the arithmetic pipeline design also. So the signed fixed point numbers can be represented either in the 2's complement, or you can represent in sign and magnitude notation. Sign and magnitude notation. So let us consider an example for this. The example for this is, let's take, I want to represent minus 7.5 to the base 10 using 8-bit binary representation. You have to represent in an 8-bit binary representation with the condition they are given. 4 digits as integer and 4 as fraction bits. So whatever the 8-bit binary number is there, so 8-bit consisting of total 8. So in that 4-bit has to be represented as integer and the 4-bit has to be represented as a fraction. So first of all, convert this number into binary number. But here they are given a signed number. So first forget about the signed number. Just take the positive value, 7.5. 7 means 1, 1, 1. And what is a 5? So decimal you have to calculate that like this, 1.0. Take only the less one, 0.0 into 2, you will get the 0. So that means you will get 1, 0. This is what. So now, this is what you get. But we have to represent it in 8, right? 8-bit binary representation. So 4-bit is the integer. So keep 0, 1, 1. So this is a 4-bit integer. And 4 fraction, 1, 0, 0. So total 8 bits. Okay, so I had converted 7.5 to the base 10, that is a binary decimal number to binary number. But you have to do the negative value. You have to find the signed value. Minus 7.5. That means what you have to do? You have to do the 2's complement. Whatever the value that you will get, perform the 2's complement on that. So how you are going to perform the 2's complement? After the first one from the LSB, all the numbers has to be complemented. Okay, don't change this one. After the first one, all the numbers has to be complement. 1, 0, 0, 0. So don't change this. You have to keep like this only. So this is what the value of this, the final value of minus 7.5 to the base 10 is. This is a binary value. So this is how the signed fixed point number is going to be represented. Okay, so this is what the fixed point. Now let's have a look on the floating point also. Let me continue here only so that we will discuss about the arithmetic pipeline design. That is the addition, subtraction and multiplication on arithmetic pipeline design in the next video. Okay. So now floating point numbers. So a floating point number, let's take x, is represented with the pair m comma e. Okay, where m we call it as a mantisas and e we call it as an exponent. Okay, so with an implied base radix. Okay, the algebraic notation of this floating point is m into r power e. So where r is the base, e is the exponent, m is the mantissa. So if you want to represent it in IEEE 754, IEEE 754 representation. So this is a standard form which is represented in the scientific notation. Okay, it's a scientific notation, a representation of a floating point. So IEEE 754. Okay, so if I take the 32 bit, so first bit indicates the sign bit, and 1 to 8, that is 8 bits are represented as mantissa, and the remaining 9 to 31, that is total 23 bits represented as, 8 bits are represented as exponent, and 23 bits are represented as mantissa. So it depends upon the circuit, it may be vary. Okay, so if you take any number, suppose 9 into 10 power 8, so here the 9 is the mantissa is 9, exponent is 8, and the base is 10. Suppose if you take the number like this, 1234.873, so the mantissa is complete number 1234.873, exponent is minus 3, and the base is 10. So this is just a floating point representation. Now let me take an example to explain this floating point representation. Okay, so how to represent a number? Let's take a 32-bit floating point number. A 32-bit floating point notation. So which is a single precision? 32-bit means single precision. 64 means double precision. So 263.3. So this is my number. I want to represent it in a floating point representation. So first take the 263, convert into binary number 100000111. How did you got this? You just do the LCM of 263, then you will get like this. Okay, so this is a binary number of 263. Now let's take 0.3. So 0.3 into 2, you will get 0.6. So take the 0. We have to take the 0 here. So next 0.6 into 2, that is 1.2. 1. Only take the integer part. You have to take only the integer part. And here 0.2 into 2, you will get 0.4. Take only the integer part. 0.4 into 2, you will get 0.8, that is 0, and 0.8 into 2, you will get 1.6, that is you have to take 1. So again it is repeating, 0.6 into 2, you will get 1.21, and 0.2 into 2, you will get 0.40. So like that it is repeating. So 1001, 1001, this is all repeating. So what is 0.3? The 0.3 is nothing but 01001, again 1001, 1001, like that it is increasing. Okay, so now step 1. I'm just explaining how to convert this number into the IEEE standard form, the floating point representation. Step 1. You will get 263.3 converted into binary number 100001111. 0100110011. So like this. Okay, and step 2. Step 2 is you have to represent it in the single precision format, that is 1.0000111. So 01001 1001. So like that it into 2 power 8. Step 3. So step 3 is convert into single precision format. What is the single precision format? First bit is the sign bit and 8 bits are the exponent and remaining 23 bits are mantissa. It's a single precision format. So everything it's a sign bit and rest of everything it's mantissa is also in the binary format only. But exponent is in still decimal format. So convert the exponent. How you are going to convert the exponent into binary number? Exponent into binary number. So for single precision, the formula is 1 into 10, 2 power e minus 127. So 2 power 8. So e minus 127 bases are is equal to 8. Exponent is equal to 135. So convert the 135 into binary number 10000111. So the 135 binary number is this. So now you got everything in the binary format. So represented in a IEEE format. So sign bit 0 and exponent whatever we got 1000011. This is exponent, sign, exponent and mantissa. So mantissa should be how many? So you have to enter 32 bits. So until 32 bits you can write 23 bits. 23 bits. 8 bits and 1 bit. So total 32 bits. So this is how you are representing the fixed point and the floating point representations. So in arithmetic design, so in the arithmetic calculations that the modern computer is going to be performed, the fixed and floating point calculations are like this. So in the next video, I'll explain what is arithmetic pipeline design. Okay, thank you.